All right, Mary is going to talk about carbon neutral concrete materials and technologies 2023, what to implement now and what is coming. Thanks, Mary.
Thanks, Shrika. Thanks for coming. Good to see you Wednesday afternoon. Kind of a rough time, but cool to see people. All right, so concrete, right? Compared to other building materials, other construction materials, if you look at embodied carbon on the y-axis here, embodied energy on the x, so how much it took to make it, carbon and cement are pretty, concrete and cement are pretty low relative to some of these other materials, and so I think a lot of people are often confused by that. You see that and you say, oh, maybe it's not so bad, and of course, we all are here for concrete, right? So pro-concrete, but it's kind of interesting to look at that. But when you consider that we're producing lots and lots and lots of concrete annually, then the carbon issue becomes big, right? And this is global Portland cement production from the 70s through more recently. You can see it's increasing, bouncing around a little bit, but it's really high, right? Over 4 billion short tons of Portland cement, and this is just cement, making up 12% of concrete maybe. So that's a lot of concrete, right, that we're continuing to produce. So the carbon footprint, you hear between 5 and 8% global anthropogenic CO2, and that's an issue. If you look at specifically what the materials are in concrete that are causing this high carbon footprint, Portland cement, of course, is one of the highest ones, right? Compared to some of the other metakaolin, slag, silica fume, etc., the aggregates, air and trainers, some of the other admixtures can be a little bit high, but Portland cement is largely the biggest target that we should be going after. So one of the questions you kind of have to ask yourself if you're trying to look at Portland cement and trying to reduce that carbon footprint is, where does the carbon footprint come from, right? Specifically, in the production of Portland cement, I think probably most of us know what this kind of situation is here. You see my mouse? Oh. All right. Anyway, so typical cement kiln, right? And we have raw materials coming in on the left, namely limestone or some form of calcium carbonate, shale, clay, various other materials. Now the kiln is kind of at an angle, rotates real slow, and there's a huge flame at the bottom, right? So as the materials go through, they start to heat up. You lose the water, eventually the limestone hits a certain temperature, and you start to lose the CO2 from the limestone, right? So that's just sort of a natural chemical reaction that happens when you heat limestone, right? But it contributes a significant amount to the total carbon footprint. In addition, those materials inside that kiln need to get to roughly 1,450 degrees C, which is very hot. So we're burning a lot of fuel in order to keep that flame at the temperature it needs to be. So those are kind of the two primary producers of CO2, or the two primary activities, I guess, that, let's say, that are responsible for that carbon footprint. So, Shrika mentioned earlier, there's all sorts of people on the case, right? We have ACI, PCA, all the letters, right, are working on this, which is good. And if you go online, which I have been, I'm working on this document, I'll talk about it in a few minutes, there's all sorts of roadmaps. Very cool, and a lot of them are generally heading in the same direction. So this is PCA's, the 5 C's, right? So start at the beginning, reduce clinker, reduce cement, reduce concrete, have more efficient construction, and then you get to carbonation. So pretty basic. This is GCCA. I think Shrika actually had it. We should have coordinated. I'm sorry. She had it in bullet points. Here it is, the graphic. But looking at sort of what do we do, right? And it's kind of interesting to look at this. I mean, I think there's, looking at, you can see that, okay, yeah. Savings in clinker production, right? So looking at the plant, what can we do there? Efficiency in concrete production, optimize mix design, optimize your aggregates, right? And those are like 10 and 11%. In the salmon, I don't know what color that is. Portland cement, right, substitution. So now we're looking at alternative cements, alternative SCMs. They're saying that's 9%. That's pretty interesting. Decarbonization of electricity. Whoops. And then recarbonation just naturally from the concrete. And then they have a huge area here for CCUS. I mean, that's interesting, I think. And then efficient design and construction. So it's interesting to see sort of what everyone is looking at moving forward. This is from the California Nevada Cement Association. I really like how they organized it. This came out in just this year. So they're looking at these emissions in 3 different categories. So the first, process emissions, saying, okay, that's sort of like the limestone calcination, right? What can we do? They're saying blended cements, CCUs, alternative cements, and clinkers. And then they break it apart into combustion emissions, saying, okay, at the plant, right, what can we do? We can burn different fuels to reduce that carbon footprint. And then further looking at waste heat recovery, renewable electricity, in terms of reducing that. So I kind of like how they organize that. But it's interesting to see, you know, looking at kind of near-term versus long-term versus mid-term solutions, kind of what's here now, what's coming. All right. So as, you know, anybody that's here that's been working on the sustainability, resiliency of concrete over however long, you know, it kind of always starts with sustainability and resiliency. And I teach a class on sustainability, and we spend a whole hour talking and saying, what is that? What is sustainability? What is resiliency? It's like they're really big concepts, right? Well, finally, or not finally, but we're narrowing it down, right? And then like Sarika said, we have to measure things, right? We have to get numbers. And so we're relying on LCAs now. We're relying on EPDs to give us some numbers so that we can make decisions based on data. And that's a really big deal. All of this is leading to the low carbon concrete code. I almost started asking questions to you like I was in class. Sorry, that would be weird. Call on people. Anyway, coming to this code, right? So there's a lot happening right now. It's very exciting. So I'm going to talk a little bit about just sort of the materials that are out there right now, what's maybe coming down the pike, and then what are some of the questions that we need to be asking as we start to embrace these new materials. So this is sort of how it used to look, right? How can we reduce the carbon footprint of concrete, replace some of the PC, replace all of the PC? Now we're saying, okay, we can also recapture some of the CO2, right, through CCUS. We're expanding it even more. How about we make ASTM C150 Portland cement, but in a different way, right? This little chart could just keep going on and on and on. There's all sorts of new stuff coming out. Pretty cool. So SCMs. So probably you're like, oh great, SCMs again. Yeah, everybody knows. But the thing is, they're here now. We know how to use them. They work pretty good. It's a pretty direct, let's get rid of the certain amount of PC, put in something else, right? Lots of different SCMs. ASCMs are alternative SCMs, so there's the classic sort of traditional ones out there, and then there's a lot of other ones being developed. There's a lot of test methods being developed so that we can use additional SCMs moving forward. That's a big deal. As most of you, I have no idea what this audience is. Probably some of you know, right? When you're looking at SCMs, they're not all the same. They're different. You have to know what they are made of, right, chemically. You have to know what the particle size is, where is it available geographically, and they behave differently, right? So SCMs that are higher in calcium tend to be hydraulic. Class C ash, slag cement are good examples of those. If you add water to it, it gets hard on its own, right? You're going to have a little bit higher replacement level with those. Also, pozzolanic, right? Many of these materials are pozzolanic. They're rich in silica or alumina, right, to form, reacting with calcium hydroxide from hydration to form more CSH. And then, I don't want to argue with anyone. Is this a filler? I don't know. This is what I put on my slide, but right, limestone is out there too as a big one, right? We know, hearing a lot about limestone, but used to be sort of a filler grinding aid. Right now we're saying, man, it does some things to the concrete. What is it doing? How does it work? Maybe it's nucleation sites, but it's a material that's going out there replacing some of the Portland cement. When we're looking at these SCMs, and these are sort of the classic or the ones that have been around, we're looking at composition. That's really big, right? Calcium, alumina, silica, where does it land relative to others? And then we can kind of get an idea of how it's going to be. So fly ash, right? Ash that goes up into the air from coal-fired power plants, of course. It's the big one, right? Most people's favorite, I would say. And it's really great, right? So this fly ash is a good example of kind of how complicated it is when you look at these alternative materials or newer low-carbon materials. So fly ash, at first glance you say, okay, I'll replace 20% Portland cement with fly ash, great. But fly ash particles are super spherical, right? They have this ball-bearing effect, allow you to maybe make your mix with a little bit less water. Okay, so now you have a more dense mix. You have a more impermeable mix. Now you have a more durable mix, right? How do you quantify that? Maybe that mix is going to last longer than the other mix, right? Need less maintenance. So there's more to it, I think, than just looking at direct replacement, right? And that's something to think about. I think we all are aware, right, that fly ash availability is changing. Coal-fired power plants are being shut down, and that's, good for the environment, maybe not so good for the concrete industry, but it's pushing us to look at other materials, right? There are a lot of other materials out there. Also, lots of harvested ash, right? So I think we've been using concrete since the 70s, or concrete, fly ash since the 70s, right? Before that, they throw it away. Since the 70s, start to use it, but they were still kind of, I'll take the good stuff and throw the bad stuff away. High carbon, high alkali, whatever, right? And now they're like, where did we put that? Right? Go get it. And so there's a lot of harvested ash out there, and really great work that's being done processing that and making it successful. So that's a pretty big one. Slag cement, of course, is out there. Works great. Not available everywhere, right? It's sort of available where you're doing steel or iron work. Sorry, should know iron from iron range. But it's not available everywhere, right? So sort of where you are matters, right? So if you're wanting to use slag but you're not near slag, to transport slag is going to really cut into your any kind of reduction. Silica fume is another big one, right? Kind of similar to I would say fly ash, right? Made from the ferrosilicon industry, tiny little particles, spherical. I think I've read twice as fine as cigarette smoke. Does amazing things in concrete, right? Tiny little particles relative to massive cement particles. You get this really great packing. You get really dense, nice bond between aggregates and paste, etc. So you get really good concrete from using silica fume. Ground glass pozzolan is sort of one of the newer classic SCMs. ASTM came out in 2020, and a lot of work has been done on glass pozzolan. So one of the things about ground glass is it's available. We're all drinking beverages, eating pickles, right, everywhere we are, and so there's glass all over the place. So it's not being produced everywhere, ground glass pozzolan, but there's the potential for maybe that to be more regional. Natural pozzolan, obviously this is not the United States, but around the world, folks are using all sorts of natural pozzolans, volcanic ash, pumice, scoria, mostly in the West here in the United States, but materials that can be taken from the earth, maybe heated a little bit, and used as the SCMs. And then we have some, I would say, ASCMs, alternative SCMs, so red mud from aluminum ore mining, some rice husk ash, right, all sorts of other materials that are out there that are being considered. And a lot of this has to do with where are you, what's available. So you've probably seen this. Karen Scrivener put this out. Actually, I gave a talk on glass pozzolans a few years ago, and then she came up and gave a talk and showed this. And then she's like, I don't even see glass on here. And I was like, fair. But anyway, availability, right? Huge. So you look at these materials and you say, okay, they're great, but there's not a lot of them out there, right? So a lot of folks are saying, Karen included, saying, what about calcined clay? What about limestone? These are the materials that are out there abundantly around the whole world, right? And so she's been working on developing the LC3 cements. So based on some clinker, right, or some Portland cement, essentially. You can't see my mouse, right? Yeah. Okay. So on the left, Portland cement, right, and then she's saying let's put in some limestone and calcined clay to replace that, either at a 50% or a 35% replacement level. So on the right here, you can see putting in the limestone, there's no CO2 emitted. Putting in the calcined clay does need to be heated, but not as hot as Portland cement, right? And so you have a lot less emissions, and so that's really taking off. Blended cements, of course, all different types, right? Blending Portland with slag, pozzolan, limestone, or ternary blends, which are sort of DIY, your own mix. I think we all know type 1L is really, is here, right? It's here. Here are all sorts of things. I'll just leave it at that. Here are all sorts of things, right? But that reduces some of the Portland cement right off the bat, okay? And it's been around for longer in like Europe, right, than here. And so every time something new comes on board, always growing pains, always sort of a learning curve. Ultra high performance concrete is a big one right now. So if you're not familiar, it's very strong, very durable, very impermeable. Can get as high as like 32 KSI. Made based on particle packing, so there's no coarse aggregate at all. It's all fines, just packed really, really tight, right? Really low water cement ratio. And you can see in the picture on the left here, it behaves a lot differently than normal concrete. UHPC, you're probably thinking in your head, yeah, but you put a lot of cement in it. Okay, fair, you do. You put a lot more cement in it than normal concrete. But it allows for very efficient design, right? So on the right, you can see on the left on the right, UHPC versus some of the other more traditional structural engineering options. A lot more efficient for the same like load or same span, right? A lot lighter, okay? Lighter means lower transportation costs, means smaller cranes, means larger clearances, right? Smaller, shallower sections, etc. So you can get a lot of efficiency that way. So when we start looking at, you know, all these materials, there's a lot to consider. All right. Alternative cements, like I said, we replace some of the cement, or we replace all of the cement. I won't read this, but this is from 242, the Committee on Alternative Cements, essentially saying that an alternative cement is a complete replacement of Portland cement, except if you need a little bit of Portland cement. But okay, so it's a full replacement. We classified the. Have I been talking for 18 minutes? That's what it says. A little bit. Okay. Clinkered alternative, calcined and non-clinkered. So in the ITG that was before 242, that doesn't matter. But we looked at trying to classify all of these different alternative cements. So there's a very wide variety of chemistries out there, which is awesome, but also complicated. You can't just say, do this for Portland and do this for alternative cements. They're all different, right? They all need to be handled differently. Calcium aluminate cements, I won't go through this whole thing here, but, our hydraulic cements typically have a lower carbon footprint than Portland cement. Applications include refractory concrete, rapid repair material. Okay, so that's the other thing to consider, is that there's a lot of alternative cements out there. It doesn't mean that they're all direct replacements for Portland cement. Okay, so Portland cement can be used in a number of applications, as you know. Calcium aluminate cements, maybe not a direct replacement. Just an example though, there was rapid repair of an airport runway in a cold climate in Norway. They had about 15 minutes for set time and got 5,800 PSI after 6 hours. So some of these cements, while they don't replace Portland directly, have really amazing properties. I'm going to go through these CSA, calcium sulfoaluminate cement, a big one. There's a bunch of magnesium-based cements. Alkali-activated cement's the one that we hear about frequently. This is probably the closest one that can replace Portland cement or be used in many of the same applications. This is a case study from Australia. They did a whole airport pretty much. They did pavements, bridge, curb, the pad. They did it all out of alkali activated concrete. They're doing a lot of work. I think they just came out with a standard for alkali activated cements in Doug's nodding in Australia. So they're moving really good on that over there. Just FYI, in case you're interested in these materials, ITG 10 came out with a report on alternative cements. There's also a practitioner's guide. The report has more, I would say, academic information. The practitioner's guide has case studies much more clearly presented than I gave, but some case studies kind of on these different materials. It offers a little bit of a review from the report, and then it also offers like a section on what do I need to consider if I'm looking at an alternative cement, right? Because there's a lot of questions that need to be asked. In addition, we just came out with an alkali activated cements report, if you want more information on that specifically. So, carbon capture, utilization, and storage, right? We saw that that was a key player in many of the roadmaps that we've seen. So, this is just from Wikipedia here. I've talked to Sarika and several other people about trying to make sure we're all on the same page, I guess, in terms of what's what. But essentially, there's a lot of companies out there right now looking at trying to pull CO2 either from a specific industry, such as the cement industry, right, directly from there, either storing it or using it somewhere, or capturing CO2 from the atmosphere, right? And the utilization goes a long way. Carbon curing, right, for mineralization, that could be with cements based on wollastonite or other calcium silicates. SCMs, some of the SCMs are ground with CO2, and some of the aggregates, the same thing. And so that is a very, very hot topic right now. I don't know if any of you guys got to the session, I think on Monday, but there's a lot of work being done out there on that. So some of the challenges as we look at these new materials, of course, testing requirements. Portland cement, ASTMs written for Portland cement do not maybe always exactly apply to some of these newer materials, right? The example is alkali activated cements might need a little bit of heat cure, okay? ASTM's C109 doesn't allow for that, okay? Otherwise it works. So, and I think ASTM just fixed that, but there's lots of questions out there, and so it's lots of things to consider. Long-term testing data, right, is one of the things that a lot of people are looking for. I think when you're looking at any kind of construction having to do with life safety, of course you're saying, where's the data, where's the proof that this is lasting a long time? All sorts of cement properties need to be understood, right, with these new materials. There's a list here. Concrete properties as well. Lots of questions to ask, okay? But I think that the companies that are out there, you know, are learning a lot from things like ACI and starting to answer all these questions. So one of the things I've been working on, I've been doing a little bit of consulting with the and one of the things I've been working on is a low carbon concrete materials company survey. So trying to reach out to all the companies out there. And if you're a company and I haven't reached out to you, please reach out to me. Be happy to have you be part of it. But we're trying to say, you know, what's going on out there? What are the companies doing? And these are some of the questions that we're sort of asking. So what's the technical readiness level? Are you starting up? Are you in lab doing stuff? Are you actually producing? When are you going to be available? Where are you available? What are you making, right? An alternative cement, a reinforcement, what other materials? What's your potential application? What's your global warming potential? Have you done an EPD? And then what's the cost, you know, roughly? And it's been really interesting to see what's coming back, and there's a lot of really awesome technology out there. So we're working on that survey. There's two parts. Part A is pretty quick, and then Part B is a little bit more in depth, just to kind of get a better idea of what you know you're up to. So again, if you haven't already and are part of a company that's creating low carbon materials, please do reach out, because we'd like to try to capture that new to kind of move on with its mission and vision. I'm also working on a strategic concrete materials guide that's coming very soon, and I hope to include all of this, and then also to include some more details on some of these newer technologies in a generic way, as well as water aggregates, reinforcement, etc. So I am really, thanks for coming, and I hope that, I don't know, it's cool you're here. I don't know a lot about all these new technologies. It's very exciting to learn. If anybody has ones they'd like to share with me, please do reach out. I'm sure you can look me up somehow, but thanks for coming. Does anybody have any questions?